So the motive behind these videos I need to share with you guys is to bridge the gap between your academics and the practical life. Imagine a simply supported structure with a UDL, uniformly distributed load on top. What is the bending moment at the support?
This is how you draw the bending moment diagram for simply supported beam with a UDL force.
My YouTube channel. This is your host Jessica with another useful and important video. No immigration, no students, nothing about immigration this time. So I'm going back to my roots, civil engineering, the subject I'm passionate about. I need to share my knowledge about the 15-16 years experience here in the UK. That's what I need to pass on to yourselves. So this is all about bending moment, shear force lecture. Basically I need to share those information. Ultimately, that was my goal when I started this YouTube channel. So the motive behind these videos I need to share with you guys is to bridge the gap between your academics and the practical life. Obviously going forward I will share some practical examples from my experience, and that's we're going to discuss here further along as well. So if you follow me through, I'm sure you will bridge the gap between your studies and when you come to join the practical life, your job. So I'm sure that will enhance your sort of ability to settle in quite easily into the practical life. Obviously this is just the start, the first lecture. All I need to know from yourself is just comment in here, was it too fast, too slow, so I can improve further on. Every day is a school day, so I can improve along. Before I let you go towards the lecture, here's a simple question for you. You need to answer, you need to provide me the answer in the comment section below. Imagine a simply supported structure with a UDL, uniformly distributed load on top. What is the bending moment at the supports? So type your answer in the comment section below. Before you watch the whole video, obviously you will find it there, but before you watch the video, give me the answers now. So let's crack on with the lecture. Thank you.
In this video, we will be discussing the bending moment and shear forces for simply supported beam. So we will discuss two cases. The first case will be for the concentrated load, and the second case will be for the UDL, uniformly distributed load. So for instance, I would draw a beam here as a simply supported beam. Simply supported means it's supported on each side, and we have a concentrated load here in the middle of the beam. So I would assume the length of this beam is 4 meters, and the concentrated load is 5 kilonewton, and the load is right in the middle of the beam. So this is 2 meters, and from that support is 2 meters. First thing first, we need to find the reaction, which is these two reactions. So I'll call this as reaction A, and this will be reaction B. So how to find the reactions RA and RB? So we know from the equation of equilibrium, summation of Fy, which is the vertical forces, must be equal to 0. So we know the vertical down direction force, we have 5 kilonewton. We don't have any RA, RB, so that means RA plus RB equal to 5 kilonewton. Actually, I left this space for the bending moment shear force diagrams, which I will add later on. So this is the RA plus RB is equal to 5 kilonewton. I'm going to use the second equation of equilibrium, which is the summation of bending moments at, for instance, we say the bending moment at B is equal to 0. So we'll take a bending moment at point B here. So we have two loads here, two reactions. So RA times that lever arm to B, which is RA times 4. That's one reaction in positive direction. And then we got this reaction, 5 kilonewton times 2, the lever arm from the B is that, so equal to 0. So this will be equal to RA times 4, which is the lever arm, which is going in positive direction, and this is in negative direction, so minus 5 kilonewton times 2. So these are the bending moment equal to 0. So from this equation we can work out the RA. So RA times 4, this is minus, so we're going to take it to the other side, equal to 10. 5 times 2, 10. So RA equal to 10 divided by 4 equal to 2.5 kilonewton. So now we know the reaction RA equal to 2.5 kilonewton. And now we already know, the first equation was this one, so we can fit this in, this value in this equation, so this will give us RB. So RB will be equal to 5, so we will take the RA to this side minus RA, so RB equal to 5 minus 2.5 equal to 2.5 kilonewton. So RB is equal to 2.5 kilonewton. Obviously this is the standard method how you find the reaction, but just in general term, I mean, if I consider this is my beam here, and I've supported on either side here, or on each end, and if you imagine there's a load here in the middle, in the center of the beam there, so definitely you will know from the logic, half of the load should go to this end and half should go to that end. So obviously if this is 5 kilonewton in the middle, so 2.5 will go there and 2.5 will go there. So straight from the logic as well, you can determine that load. This is a really simple sort of case, but obviously when it comes to complicated loads, then this is the way how you find the reactions. So now we have RA and RB reactions here, and now we're gonna try to draw the shear forces. The shear force, you need to remember, is always maximum at the support. So shear force maximum at support, and you need to remember bending moment is maximum at center of the beam. If I draw the bending moment shear force diagrams here, so just imagine, just draw a straight line here. So we'll start from the left hand side for the shear force. So this is for the shear force. So you can see from the left hand, RA is acting up 2.5 kilonewton. So this will go up 2.5 kilonewton. And you can see there's nothing there, no load here until we reach here the 5 kilonewton. So we go another point here, the middle. So there's no load, so it will go straight. The shear force will be exactly the same throughout this length until we reach there where we got the 5 kilonewton. So the 5 kilonewton is pushing the beam downwards. So 2.5 kilonewton here, and it will push down 2.5 kilonewton here. So the total here is 5 kilonewton. So 2.5 kilonewton the top, and is pushing further. So the total here is 5 kilonewton, which is coming from this load. And again, further down, basically past this 5 kilonewton, there's no load here on the beam, so this will go straight here to the end, and from RB, which is pushing the beam up, basically the reaction here, so it closed the loop. So this is 2.5. So this, now we have drawn the shear force diagram. So this is the shear force diagram, and you can see in the middle of the beam, center of the beam, it's 0. Shear force is 0, but at the supports 2.5 kilonewton and 2.5 kilonewton. So it generally it cancels out, actually 2.5 there, 2.5 there, so it's 0. at the center of the beam, and at the support we got 2.5 kilonewton. Now we're gonna try draw the bending moment diagram. So we'll draw another straight line. So there are certain ways, I mean, you can draw the bending moment diagrams. The easiest way is obviously we got the concentrated load here. So first we can straight away find out the bending moment for this case. In this case here we got the point load, so the bending moment will be, we'll draw here, the bending moment for point load will be PL/4. So that will give you the maximum bending moment in the simply supported beam for the concentrated load. So P in this case is this load P. L we already know is 4 meter, and divide by 4. So if you feed all the details here, so 5 times 4 divide by 4, so we will left with 5 kilonewton meter. So this is the maximum bending moment in the simply supported beam with a concentrated load in the center of the beam, which is, as said earlier, the maximum bending moment is at the center of the beam. So the center of the beam is here. So this will be the maximum bending moment, 5 kilonewton. So here at the support, we always have 0 bending moment for simply supported case. So this will go this way, 5 kilonewton and 5 kilonewton coming back. So this is the maximum bending moment, 5 kilonewton meter. And also you would see wherever we got the 0 shear force, we will always have the maximum bending moment at that point. So that's another check as well. Also another way to find out, yeah, this diagram is from the area of the shear force diagram. So for instance, if we got this bending moment here, so this is 2.5, so this length we got 2 meter. So 2.5 times 2 is equal to 5 kilonewton. So this is 5 kilonewton meter, and again, yeah, this area is this area, basically 5 kilonewton meter. So you can find, yeah, the bending moment from the shear force diagram as well. So that's another way you can figure out here the shear force and the bending moment. So I hope, guys, this is clear now. Obviously I've tried to explain it from the standard way. This is really a simple case. You may encounter some different sort of loading there, and in that case definitely you will need to use the method, the summation of equilibrium equations as to find out the reactions and the shear forces bending moments. So let's start with the second case, a simply supported beam. So I'm gonna assume exactly the same length and same loading, but a UDL. So reaction here, reaction there. So it's a simply supported beam with a UDL in this scenario. So I will imagine this is a UDL, uniformly distributed load. I'll use the same magnitude, 5 kilonewton, but in this case per meter, and I will call it W. The length, I'll keep it the same as previous, L equal to 4 meter. So in this scenario, obviously we know the load is UDL, so this is slightly different scenario for the bending moment, which is previously we said PL/4. In this scenario we would have a different formula, but first thing first, we need to find out the reactions at the end, and we can again simply use the formula which we used there previously, summation of the equilibrium equations, or alternatively, as said previously, if we go the beam simply supported and we go the UDL, which is uniformly distributed load throughout the length. So by logic, half of the load should go to one support and half of the other should go to the other support. So we will use that logic here. So in this scenario, we got the 5 kilonewton per meter. So how to convert that basically to a point load? So simply you can see the unit here, kilonewton per meter. If we times that with the length, which is a meter, so we will get the P. P is actually the concentrated load. So to convert that UDL to P, the point load, so P would be equal to W into L. So W is 5 and L is 4. So we got 20 kilonewton. So if I add the units here, kilonewton, this is very important, guys. I mean, you need to use the units here to make sure you are doing the right thing here. So you can see that for 5, we got the unit 5 kilonewton per meter, and the length is 4 meter. So that cancels out, so you left with kilonewton. That means we have converted that UDL to a kilonewton, which is the point load here. So now you got the 20 kilonewton load instead of the W 5 kilonewton per meter, basically the UDL. Now we have converted that to 20 kilonewton concentrated load, acting as if in the middle of the beam, basically. So instead of that, we can use 20 kilonewton. And now imagine, yeah, this is in the middle of the beam, so half of this will go to RA. So RA would be 20 divided by 2, which is 10 kilonewton, and similarly half will go to the RB, 10 kilonewton. So simply you have figured out the reactions here, and now we're gonna find out the bending moment. So for the UDL case, again, this is a simple formula, WL square over 8. This is a simple formula you can use for finding out the bending moment for the UDL case for simply supported beams. So W we got in kilonewton per meter, so 5. L we got 4 meter, so I will use 4 square, so L square and divide by 8. So we'll use that. So 5, 16, 80, 10. So we got 10 kilonewton meter. Again, guys, this unit, you need to ensure you get the right sort of values here. If I use the units here in this formula, let's use the units here. So for W we got the unit is kilonewton per meter, and then times L square. L square is meter square. So you see, kilonewton meter times m square, so that cancels out, so you left with kilonewton meter, which is the unit for bending moment, kilonewton meter. So this is very crucial. Another important thing is about the units. Again, if this is in millimeter, you need to ensure you convert that to the same unit as the loading, or vice versa. I mean, if this is in Newton per millimeter and this is in meter, again, you need to ensure you use consistent units here to work out the bending moment. So now we know the maximum bending moment, 10 kilonewton, and now we know the reactions here as well. So let's draw the bending moment and shear force diagrams. Actually, I'm not left much of the space there, or try to squeeze in. So this is for the shear force. So here we go, RA 10 kilonewton, 10 kilonewton, so going up reaction. But now until we reach to the middle, there is basically a UDL, 5 kilonewton per meter, that pushes the beam actually down. So we go up, and this needs to come down basically to the center, because this UDL that's pushing, this is pushing the beam down until we get to the center here. Again, past this middle, again is pushing the beam down until we get to the RB, and that pushes the beam up. So this is how you get, and this pushes it up. So this is 10 kilonewton, this is 10 kilonewton, and see in the middle you get 0 shear force. So you got this shear force diagram. And now to draw the bending moment diagram, again, as said, the maximum would be wherever we get the minimum shear force, the zero shear force here, so we would have the maximum bending moment there. Again, you can use the area method, so you can use that area of this triangle, so that will be the bending moment diagram here. But obviously we already work out the bending moment here, 10 kilonewtons, so 0 at the end, 10, and this is negative, so it will come back to 0 there, and the maximum is 10 kilonewton meters. This is how you draw the bending moment diagram for simply supported beam with a UDL force. Thank you very much for your time, and I hope to see you in the next video.